All right, good evening, everyone. Tonight we're going to dive into the magical and often misunderstood world of. This will be the first of 3 study groups on time series. So tonight we're going to focus kind of on the basics, visualizing time series, understanding the concept of stationarity, knowing what trends and seasonality are, using differencing, and also utilizing ACF and PACF graphs. So what is a time series? Is anyone able to answer this right now? Does anyone have a general idea?
Any kind of data over time?
Yeah, that's one way to put it. So it's basically any data that has a consistent distance between the x values. So data that's sampled at every month or every week or every year. So it has a set distance between each of the x values and it increments that each time. So we'll go ahead and make a time series right here. And plot it. So you'll notice a couple things just in the code first. So most of the time series you're going to work with, you're going to put them in a data frame. To work with time series in pandas, you need to make the index be time. And if you notice this line here, you need to set it to a date time index, the index object itself. So this just generated this time series, so we can see it's from 2008 to 2018. In this case, it's by month. You could see that if you printed out the data frame, but we can see how a value would change over time. So it contains continuous values with a consistent frequency or equal intervals between them. So the concept of stationarity, this is really important when dealing with time series because it's something that's necessary to work with a lot of modeling techniques. So we can say a time series is stationary if it meets 3 conditions. So it needs to have a constant mean, a constant variance, and constant covariance over time. So we'll take a look at this graphic here to kind of see what that means. So the first part here, on the left is a stationary series, on the right is a non-stationary. It's non-stationary because the mean increases over time. So if we drew a line through where the mean is, let's see. So on this one, it would be a straight line across, but on this one, you can see that it's increasing. So this would not be stationary. For the second one, this one's stationary here, because basically the variance, so the amount that it differs from the mean, is about the same. It stays kind of consistent over time. Here, if we draw a baseline, we can see that we have this distance here, but then it goes out wider here, and down here it's a little bit wider as well. So this one would not be stationary. And then lastly, on this one, we can see that basically the distance between like the curves here on this one is consistent. So we have like consistent spacing. And then on this one, it gets shorter, closer together, and then spaces back out again. So this one fails because of the covariance measure. So I have a little exercise here then. So which of these series are stationary? And if they're not, what do they violate? So Bonnie, can you tell me this one here, TS2, is this stationary or non-stationary?
TS1 can be
TS2.
Oh, TS2 is not.
Okay, and what does it violate?
The mean doesn't look like to be the same over time. And also, yeah, I would say the mean.
Okay, yeah, predominantly
I tell from the variance.
Yeah, the variance might differ too a bit, but most obviously it's the mean. Okay, what about TS3 here? Juliet, what do you think? Is this stationary or not stationary?
I'm gonna say that is non-stationary.
Okay, and why?
It looks maybe like the variance is not constant. Maybe. Yeah.
Right. So here we can see it sticks out like a little bit, but then up here it's out a lot. So yeah, the variance changes over time. It's not consistent with both sides of the mean. All right. So on TS4, Brendan, what do you think for this one?
It is not. The variance changes over time, or is a function of time, I guess.
All right, good. And lastly, this one, Jacob.
Not stationary.
Yep. And what does it violate?
Variance or covariance.
I think this one would technically be both, variance and covariance. You'd probably have to see a little bit closer, but it looks like it's basically getting tighter. The distance between the like seasonality of it is shorter in the middle.
Okay.
All right, so that's basically stationarity. Whenever, for most models for time series, they assume that your time series is stationary. So we have a couple tricks that we can use to make a non-stationary series stationary. But first of all, to statistically determine that a time series is stationary, we have the Dickey-Fuller test. So this is a hypothesis test, our best friend. It's used to check for stationarity of time series. The null hypothesis is that the time series is non-stationary, while the alternative hypothesis is that the time series is stationary. So if we get a low p-value, we reject the null, and we can say that the time series is stationary. So importing this then, we get it from stats models. And we can go ahead and just print out our time series data frame to have an idea of what it looks like here. All right, and it's really easy to work with. You just have to pass in a time series. So you have a date time index and then a column with values. And if we pass that in, we get a results object. The first value is the Dickey-Fuller statistic, and then the second value is going to be the p-value. So here we can see, so this was our, let's go ahead and just plot this here so we remember. Series.plot. So this was our time series. So did we think this would be stationary?
No.
Why not?
Oh, this one? It looks
this one here.
Okay. This one probably is.
Yep, so this one's basically perfectly stationary. I generated it from like a sine wave. So, you know, it's pretty much a perfect curve here. So in this case, we get a 0 for our p-value, actually. So this is definitely stationary.
Mm-hmm. Okay.
All right. So now we're going to make another time series that's a little bit different. And you'll see why when I plot it. So now we have this time series. It looks similar to the first one we did, but a little bit different. Do we think this one's stationary?
No.
And why not?
The mean is not the same.
Right, so if we draw a line through the mean, we can see that it increases over time. So how would we make this stationary? First of all, just to confirm, we'll do the Dickey-Fuller test. We can see very high p-value, obviously not stationary. So to make it stationary, we have two main options, differencing and transformations. So we're going to start with differencing. Differencing is at each step in the time series, at each date, each month, or whatever frequency we have, we subtract the previous value at a given interval. So for example, if we do lag 1 differencing at each time point, so say we have these dates here, and then we have some values. So this is the base data. If we wanted to make the lag 1 data. So since our first one doesn't have anything before it, it basically, we just cancel it out. We don't worry about it. But our second point, we can take the value at this point and subtract from one previous period. So we would take 8 minus 5 and we get 3. And then in this one, we could take 12 minus 8 and get 4. So you'd basically do this across the whole data frame. And we'll see what it does here in a second. So yeah, for each data point, you subtract the previous data point.
Can I ask a question?
Sure.
So it seems that we assume that a stationary time series is better. Why is that?
So you'll kind of see why here as we talk about some of the models. But for right now, basically you just need to know that models won't be able to accurately model the changes in the time series if it's stationary. Basically, if we give a model a graph that looks like this, it won't be able to account for this upward trend. So when it goes to predict, let me just get a different color, it would likely predict something like this. So it wouldn't be able to account for that trend upward. But if we first make the time series stationary, like so, then the forecasted model would be a lot better at picking up that trend and modeling it. So it'll make more sense as we go on, but for right now, it's just kind of a necessity. So if we go ahead and print out a data frame here of our time series, we can see our values are just the X column. So now we can make a column called lag1, and the really easy way to do differencing is to just the data frame or series object called .diff. You can pass in an axis if you're in a data frame. If it's a series, you don't need to do an axis because there's just the one column. And then periods is how many lag difference do we want to do. So the default is 1, so you actually don't have to put periods equals 1, but if you want something higher, you'd have to put a value there. So now if we view this, we can see the first value, there's nothing before it, so it becomes null. One of the ways to fill this is just with, you either fill it with a 0 or you just drop it completely. But you can see all these next values, it just took the difference from one point and the previous. And now you can see the values are all much closer together. And then if we go ahead and plot the lag1 difference time series versus the regular data, we can see that now it's become stationary. So you can do lag up to any number of differencing. So often 1 is the most popular. It will help a lot with linear trends like we saw, but you can difference basically any number you want. So we'll make another time series here. So we can see this one looks a little bit funkier. Probably won't be the same as the two examples we've been working with. So we can go ahead and try and do a single difference of this, try and make it stationary and plot that. And we can see that clearly something went wrong here. It definitely violates the variance stipulation of stationarity. So that didn't work. But actually, if we try a lag difference of 2 and then plot it, this does make it stationary. So now, how could we have known that just by looking at this plot here? Well, you technically couldn't. A way to figure out how much differencing you need are from two graphs known as ACF and PACF. So it's autocorrelation function and partial autocorrelation function. They basically tell you more about what's going on in a time series by plotting a time series versus different lags. So the difference between the two, the autocorrelation, the ACF, just measures the absolute relationship between points and various lag amounts, while the partial autocorrelation function, PACF, measures only the current lag you're at and not other lags. So something that ends up happening, say you have a time series that needs to be differenced by 2, often on the ACF, you'll see significant stuff at 2, at 4, at 6, at 8. So it kind of propagates throughout the rest of the time series. But with PACF, it would kind of remove that relationship and you would only see significance at 2. So we'll take a look at what these are. I just want to preface this by saying that ACF and PACF are probably two of the hardest tools to use when it comes to time series. There's a lot out there on how to read them, what you can gather from them. Sometimes those things disagree. So take this all with a grain of salt. I'm also going to provide a lot of other resources to kind of consult and to make sense of this. But we'll look at kind of a simple example of how to use these here now. So this is what ACF is basically doing. So it's plotting the base function, and then it starts off with lag 1, plots it against itself, and sees how much the 2 line up. And then it will do this again with all the other lags. So it'll even do up to 7. It'll measure how much these 2 line up. You can see for 7, it's not going to be very much. So to plot these, you get it from stats models here. Just plot ACF, plot PACF. We'll import that. And all you have to do is pass in a time series. So just a date index and then values. And we'll go ahead and plot both of these here. So this is generally what they look like. You're going to have values from 0 to 20 or higher, depending on your time series. And then you're going to have this blue region. The blue region is basically like a cutoff. So anything outside of the blue region is significant. Anything within it probably can be ignored. So when we look at this, remember we ended up differencing ours by 2. So on the ACF, we can see that this would be lag 1, this would be lag 2. So for lag 2, we have the highest and most significant autocorrelation. And then what happens on the PACF is that we have 2 being really high, and then it immediately goes negative. So this is kind of a trend you'll notice. If there's differencing that needs to be done, you'll often have on the PACF a positive value that's pretty high, followed by a drop-off. That usually tells you that there's some differencing needed there, but not always. So that's kind of how we could have determined to do a differencing of 2 for that time series. So you can actually chain multiple differences together. So you can do a difference of 1 and then a difference of 5, and you could even add more on after that. And a property of this is that the order does not matter. So for example, if I do a lag 1 and then do a lag 3, my data here will be exactly the same as if I did a lag 3 and then a lag 1. So the order doesn't matter. Often what you'll do is you'll do one difference, you'll see how it changes the plot, see how much, if it makes it stationary. If that doesn't work, you might add another lag, and sometimes 2 does the trick, sometimes it's 3, it kind of just depends. So to get an example of that, we'll make another time series, this one here. It's definitely not stationary. We'll go ahead and plot the ACF and PACF. And does anyone have just like a random guess on a lag n difference that we should take for this? So we want one that has a high peak on the ACF and one that has a high peak followed by a negative peak on the ACF, PACF. Does anyone have a guess or two? Bonnie, what about you?
Four?
4, okay. Why do you say that?
Wait, are we looking at the highest positive and then followed by a highest negative?
Yeah, so on the first one, the ACF, in the previous example, we saw the highest peak at the difference that we needed.
Mm-hmm.
And then on the PACF, we saw a high peak followed by a flip to negative values right after.
Right, so the negative value, does it need to be significant?
So in that case, no. It's just usually you'll have a significant positive value on the bottom one, and then it immediately flips to being negative.
Okay, so maybe 3.
Okay, that's a good guess. On the ACF, we can see it's pretty high. So we could try 3. That's the first one I was going to try. So we'll go ahead and use the difference. We'll plug in periods equals 3 and plot it. So what do we think? Did this make it stationary?
No.
And why not?
The variance and means still change.
The mean's pretty close to being constant, but yeah, the variance definitely. We can see from one end to the other, there's definitely like an angle here going on where it changes. So we're not done. So we might need to do another difference. So what we can do is we can take our difference of 3 time series and plug that into our PF and PACF. So this will remove that lag difference of 3 and let us know what's remaining. So you'll notice I added something here called, it's not highlighting it right, but B-fill. So remember what I said, that when we do like lag 1, for example, first value is basically null because we don't have a value before it to difference. It's similar when we have like a lag 3. So say we have, our different points here. So if we wanted to do lag 3, we would have to start at the 3rd value and subtract, or no, we'd have to start actually at the 4th value and subtract 3 values previous. So in lag 3, the first 3 values are going to be null, and so on and so forth for any lag value. So what B-fill does is basically fills in that null value because you can't plug in a null value to this plot ACF, plot PACF function. So that's what that does. All right, so here's our difference of 3, ACF and PACF. So from this, if we had to choose a second difference amount, what would we choose?
Five, maybe?
Yep, that's a good guess, because 5 is the highest point here, and on the PACF we can see 5's pretty high, and then it immediately goes to negative. Also, something you can kind of notice is that usually multiples of a significant lag will be high too. So we can see 5, 10, 15, 20, all of those are significant. That all gives like a lot of evidence that yes, we probably should also do a difference of 5.
So I have a quick question. I'm sorry.
Sure.
So we want to make sure that do the numbers have to be the same in the ACF and the PACF? So like, let's say that we chose 3 or like 1 in the first one, but then it showed that 3 was better for the PACF. You know what I'm trying to say? Does that make sense?
Yeah, so usually you'll just want to decide on one number. So
Okay.
probably the number that has the most significance for both. It's kind of more complicated than that. Like these time series are like manufactured to be kind of easy to detect this. So when you get a real one, it's going to be a little bit more hazy on like where to make that distinction. But yeah, you usually should see the same stuff on both at the same lags. So if there's something going on in the ACF at lag 5, odds are there's something on the PACF going on at lag 5. So we'll just go ahead and plot. This is still the lag difference of 3. And then, and then we want to just chain on here. So dot diff periods equals 5. So remember what I said, you can chain on the difference saying order doesn't matter. We could switch these around. So we'll go ahead and chain on the 5. And now what about this? Do we think this is stationary enough? Yes? No?
I feel like it can be better.
Probably could be better. But what you'll notice, if we were to run like the Dickey-Fuller test on this would probably be stationary. It kind of just has to roughly be there. The larger your data, the more leeway you get, basically. If we had a short time series, like 1 year long, then it would really have to look stationary. But the bigger the data set you get, kind of the more leeway you get, if that makes sense. And so one more thing just to point out here. Another thing we could have tried, since both 3 and 5 seem to be significant, sometimes this does the trick, just combining them together. So actually doing 15, so 3 times 5. So if we do that, actually, we get a really good stationary plot. So that's something to think of. Sometimes if there is a lag of a high value, like 15 or something, odds are you'll see significance at its multiples. And usually that can lead you to the conclusion that maybe you just need the larger value as your singular lag.
Question.
Sure.
So the ACF and PACF, is there a table to show the numerical values? So we're not just telling by the graph, but maybe there is a number we can see, like a p-value or MSE kind of thing.
Yeah, that's a good question. I think there probably is. It's not going to be off of that function because it just plots it.
Okay.
I'll have to double check on that, but there probably is. Usually you can just tell though. Sometimes you'll get a chart that goes out to like, I don't know, 300 or something, and then it gets kind of too small on the x-axis, but you can just kind of limit it, what you can see. But yeah, let me check on that. I'm sure there is something that just like puts out it in like a table form.
Cool, and I kind of lost just now. So just to recap, when we do the second step, we are looking for the same pattern, right? Similar pattern. And we basically just do a chain lag.
Right. So
Okay.
you basically find one significant lag, you can remove that, see what you're left with, and then kind of go from there until you get something stationary.
Cool.
And then I was just saying that since we had lags at 3 and 5, we could maybe try 15, because maybe it's actually 15 is the overall lag, since it's just kind of multiples of 15. So it's kind of, you have to try things out and see what works. There is some strategy involved. There's like guidelines. I think there's a table in the curriculum that kind of tells you, oh, if it does this at this value, maybe try that lag amount. But you kind of just have to try it out and see what happens to the time series. All right, so that was differencing. That's one way to make a time series stationary. Another is transformations. So this is just like when we were doing linear regression. So like, you know, you can have a quadratic transformation, a log transformation, so on and so forth. So we'll make a time series here. You can see it has a trend, but the trend kind of, you know, curves up. So it's not linear. So if one way to print out and view that trend without just like drawing over the graph is to use the rolling mean. So this basically, we have our time series here. You'll pick a period, so you know, maybe over a year, maybe over 6 months, and it will calculate the average at each of those points, and it will kind of smooth your line out. So in this case, we can choose a window of 12. So our time series is in months, so that will be a year. So at each point, it will calculate basically the mean for a year's period, and then it'll plot that out here. So you can see it kind of smoothed the line out. It allows us to more clearly see the trend that's going on. And we can see that it does indeed kind of curve upward. So we know we're not dealing with a linear trend. So differencing probably won't work. So in this case, we need to do a transformation. We could start off with a log transformation, basically just passing the time series into numpy.log. And then we'll also plot the rolling mean so that we can check our trend. We're basically trying to get it to be linear. And so we can see with the log transformation, it changed it, but it didn't really make it linear. It's still kind of curving upward. So we might have to try something else. So we could do a square root transformation. And if we go ahead and plot that, now we can see our trend line is a lot more linear. So we could go with this one. So now we basically have a linear time series. So we could try differencing it now. So basically, we replace our time series with the square root transformed version. And then we're just going to do a difference of 1 and see what happens. We can see it leveled it out. There is still some variance discrepancy. It's higher at the beginning and less at the end. So it may not be fully stationary. So something else you can actually do is subtract the rolling mean. So in this case, we have our square root transformed series, and we're subtracting the rolling mean for each year from that series. So this is basically another form of differencing, except you're subtracting a mean instead of just a previous value. So if we go ahead and plot this, you'll see what it does. It does almost the exact same thing as just taking the lag 1 difference. So in this case, either one would be valid because it kind of gives the same result. But we can double check now that we have this time series, whether or not it's stationary enough by using the Dickey-Fuller test. So we'll go ahead and print that out. We can see the p-value is significant enough for us to reject the null. And we can say that this time series is in fact stationary. Like I said, even though it may not look like it, once you get enough data points, it can kind of look less and less stationary and still pass the Dickey-Fuller test. So in that case, we would have made that time series stationary. So now one last tool that can kind of help you figure out what's going on with time series is seasonal decomposition. So this code is from the curriculum. It basically uses the seasonal decompose function from stats models to break down your time series into its trend, into seasonal components. You know, if it has a curve that kind of repeats like a wave, and you'll see what it looks like here. So actually go back. Then we'll have to exit out because it's a big chart. Can you guys see this okay? Yes. Is it off to the left-hand side for you guys too? Yeah, it probably is.
Yeah.
For some reason, the slideshow always does this to my notebooks. So basically, let me pull it up here. You might have to just do this on your local notebook to see it clearly. Okay, but so the first one is just the original time series. The second one is going to be the trend. So we could see this is basically the line that we drew through the mean, or what we calculated with the rolling mean. Then you have seasonality. So usually there's a seasonality component to a time series, so something that repeats over a certain interval. So here we can see there's a yearly seasonality going on. And then lastly, there's just going to be some noise or residuals. So just little perturbations that kind of aren't explained by the trend or seasonality. And this lets you kind of break down a time series that might look really big and scary and, you know, figure out, okay, there's definitely a linear trend, or there's what appears to be an exponential trend. And then you can check if there's seasonality involved. That can kind of help with differencing as well. So let me go back to the slideshow here. So for the activity, there's some sales data in a CSV. You're basically going to open it up you're going to have to make the index the date and convert it to a date time index. And then you can plot it. You can do the seasonal decompose. You can plot the ACF and PACF. And you're ultimately going to decide if there's any trends. Is the series stationary? And then if it's not stationary, figure out a way to make it stationary. So with that, does anyone have any questions?
I have one question. I feel like
Okay.
maybe I missed it. I don't know. But for differencing, that's when it's linear. We can't use it for any other one, right? Like we want to make sure that we turn it into linear before we start differencing.
Right. You usually want it to be a linear trend, and then you can do differencing. Yeah.
Okay. Thank you. I thank you.
All right. Anyone else? All right. I'm gonna pause record.
Alrighty, first we imported the CSV and saw that the date wasn't in the date time format. So we just passed in the date column as an index and just dropped the regular date off, plotted it to see if it was stationary and saw that it wasn't around the mean. So we tried to do a transformation with the rolling mean on the square root transformation, and we just picked a 12, a window of 12 just randomly, but we ran the Dickey-Fuller test and saw that it rejected it, so it was standardized after that or stationary after that. And the second way we did just using the ACF and the PACF, and we saw like around 7, it seemed like, a significant period. So we used that in the difference down here and saw that it kind of corrected it. Not too many positives, 1 negative here, 3 negatives there. And we plotted it to see and used the Dickey-Fuller test to confirm if it was enough to reject the null, saying that it was stationary. That's it.
All right. Thank you.
So Jacob, you did a transformation first and then did the lag, correct? Or it's separate?
We did the transformation and then we subtracted the rolling mean from that. It was the first method we did, and since we finished that early, we just tried the second method where we looked at the graphs first and chose the periods on the difference.
So the stationary plots is after transformation and after the subtraction, right? Can you go back to your code? Sorry.
Yeah. Hold on. Let me share my screen again.
So if you can scroll down.
Scroll down.
Yeah. So you did transformation first. Oh, and so this is already stationary.
Yeah.
Okay.
We just got lucky here because at first we just did the rolling.
Yeah.
Without the difference in the rolling mean, and it was still pretty much the same graph here.
Right.
So we tried the square root difference with the rolling mean and saw that it was stationary.
Got it. And your lag is a separate, so that's also stationary.
Yeah, we did this one here.
Okay.
Just starting looking at the graphs first to figure out what period we would use, and plugged in the period there and looked at the graph and then used the Dickey-Fuller test to confirm. that it was stationary.
So Matt, I did try the seasonality one,
Mhm.
and the third graph, the seasonality one showed stationary. So that one, how do we test that one? Like, how do we, is it just seasonal?
So you did the seasonal decomposition, and then you're just
Yeah.
looking at the seasonal component.
Right.
So that just tells you if there is like seasonality going on. So I think in that graph you'll see that it's weekly basically. So there's this like weekly pattern.
Right.
So that could have led you then to choosing the difference of 7 as well.
Okay. So this chart just like shows you what lag you should use.
Yeah, it can. It's kind of just to let you know more what's going on, like because you can't see that seasonality just from looking at it like overall.
Right.
Yep. So can you guys think of any benefits or like negatives over these two methods? So if you're doing the rolling mean versus just differencing, so if I was going to use both and then go and try and make like a forecast to like predict into the future, can you guys think of any reasons why one might be better than the other? Anyone? So in the rolling mean, we're taking, you know, a window of 7, 12, whatever, and we're condensing all that into just the average. So are we kind of like losing information in that way then?
Mm-hmm.
Yeah.
Because we're kind of pushing it all together. So depending on like what you want to forecast then, like if you need to forecast the daily, then you can't really do a rolling mean like weekly because you're not going to be able to then to break it back out. So if you can do differencing, it's probably preferable to do that instead of the transformation and then difference of the rolling mean. But you might end up with time series that are like too complicated for just simple differencing, and you'll have to do something like the rolling mean. And the rolling mean is also what's known as resampling in a way. So you're basically changing the frequency between the data points. So you were going from it's daily to it's now weekly. And you can also do that just off of a pandas data frame. I think it's like dot resample or something. And you can put in a different frequency. So if it's monthly, you could make it weekly now or daily. So sometimes that can come in handy, you know, if you're only trying to predict monthly results or something, you don't really need to know what it is weekly or daily. So you can condense it in those situations. All right, does anyone have any questions? Hopefully tonight's just kind of like a warm up for you guys. Wednesday, we're going to actually build some models that can do predictions. It's probably going to be pretty heavy, but tonight kind of gives you the foundation to be able to do that stuff. So how did you guys feel about this? Like, you completely understand it or kind of iffy or not at all?
I feel good. I feel good.
I just have a question. I'm sorry. Oh my God, my thing is so annoying. I just have a question. How do all right, so I got the rolling mean one, right? But then using the ACF and the PACF, how do I get the plot to show, like after I found that it's 7, how do I get the plot again? I guess I missed that part. Like to see that
so then you do the difference of 7 and you pass that differenced time series into the plotting function.
Inside of the, okay, so then this.
So you add on the dot diff, and then you also have to add the backfill, the vfill.
I got it. Okay, I was missing that part. Gotcha.
Yep.
All right, thank you.
Yep. All right, any other questions, concerns, comments before we leave?
Can you explain the B fill again?
Right. So say we're doing a lag 1 difference. Our first value, we can't subtract the day before, the time before, because there isn't one. So it ends up being a null value. You'll see it in your data frame for your series.
Okay,
Yeah, so the B fill fills it in. I forget if it does like an average value or if it just does like 0 or something. But it basically just makes it so there's values there and there's no nulls.
Right. That's why I did not put that one and I received nones. Right.
Yep.
There's a F field, right?
There might be.
I think I was seeing it on like some of the readmes using F field instead of B field, but I forgot what it was for.
I think maybe if it's at the end of the data set, like backfill might use the first couple real values to kind of fill in the first few. I'll have to check the documentation, but
Yeah. Or I think it goes with that resampling you're talking about. If you like go from monthly to like weekly or like daily to, bi-daily or something, twice a day, and you only have one data point. So you'll forward fill those null values and with the current day value or something like that. I don't want to get anyone lost here.
No, that makes sense. And that reminds me with the resampling, I think there are a couple different ways you can tell it to do it. So you could either, if you wanted to go from say weekly to monthly, you could either have it take the average of the weeks in a month and have that be your value, or you could just have it take the first of each month or the last of each month as the value. So I think there's like different options there. All right, I guess we'll call it a night here, finishing kind of early for once, so that's a good thing. I will see everyone Wednesday.
Thank you.
Bye.
Thanks, Matt.
Bye.
Bye. Why can't I?